Hello, welcome to the second part of the 10th lecture in ML series. In this lecture, we will be discussing gradient descent method. Gradient descent method used by the machines to learn the parameters of a linear regression problem. Initially, it starts with random parameters, and it works by checking how wrong the prediction is, and then taking small steps to reduce the error again and again until it gets better. This method is used when a direct solution by normal equation is costly or it is not possible for non-convex functions. This is an iterative method. So an intuitive way of understanding gradient descent method is: imagine you are at the top of a mountain in a dense fog. You cannot see the path, but you can see the slope, and your goal is to reach to a bottom. So what you do is you take a step in the direction of the steepest descent until you reach to a flat spot. So in this the similar way gradient descent also works. Always you move in the direction of the steepest descent. Okay, so and how much step that you take is decided by some parameter called a learning rate that lies between 0 and 1. And so let us consider an example. Suppose you have this initially at this part, and you move in the direction of the steepest descent, and you continue, and it will end up here. Okay, so now let us try to understand so now initially it starts with a random parameter values, and in each step it will be updated by using this equation, that is theta j is theta j minus alpha into dou by dou theta into j of theta. This is actually a slope. So this updation is done simultaneously for all theta. So first you calculate dou by dou theta into j theta, dou by dou theta j theta. So that is a partial derivative with respect to theta j. So that is nothing but so 1 by 2 will cancel out, and you get sigma I is equal to 1 to m, the predicted value minus actual value into xj of I. So that xj of I is 1 for I is equal to 0. Okay, so this is the equation. So that the theta j is theta j minus alpha into 1 by m, sigma is equal to 1 to n. The predicted value minus the actual value. If you recall the definition of error, that is actually the difference between predicted and actual value. Now if you take sum of all that is sum over all training examples, the error, the total error is this factor, and if you multiply that one with the xj value, that is the factor that you need to subtract from a theta j to update the theta j value. Okay, so that's what and there is an important parameter here alpha, that is the learning rate, that controls the size of the each step, takes down the gradient. Now so what happens when, suppose we consider a single parameter theta and j theta, so that is actually a parabola kind of a thing. So we have error surface as parabola, and so if he initially starts at this in the steep in the direction of the steepest descent, so it moves in this direction, and how much it has to be moved is decided by using this alpha value. If the alpha is too low or a too small value, then it takes many iterations to reach to the minimum value. If it is too high, what happens is it may overshoot and it may fail to converge, or it may diverge also. It goes in the opposite direction of the mean. Okay, so we have to choose. I think this is something that we have to experiment and then decide some alpha values. Okay. So generally you start with 0.01 and then you change it to 0.01 based on how it is learning the parameters. And let us try to understand this one with an example. So we have this example of the study hours versus exam score. You are given this data set, and then by using a gradient descent method we have to find the parameters theta naught, theta 1. So as we know that initially starts with some random parameter values. So in this example we consider the random parameter values as 1, 1, and we have to choose one learning parameter, and then we have to repeatedly update these theta values. Okay, so we have considered the initial values as 1 and 1, and the learning rate as 0.01, and we have to update. So for updating you can consider, so this factor is simply the total error of our all training example, that is sigma I is equal to 1 to m h theta of xi minus yi is the, because h theta of xi minus yi is the error, the total sum over all training examples. So 1 by m into 1 by m into alpha, and similarly if you multiply with xi, that error over each example multiplied with that xi, and then total over all training examples, when you do 1 by m you can update theta 1. The current hypothesis is 1 plus 1 into x, because theta naught is 1 and theta 1 is 1, and we get an error because when you substitute 2468 value, then we'll get, these are the errors, minus 57, minus 70, minus 78, minus 86, and you can calculate the total error, that is minus 290, and each error multiplied with respect to xi, then we'll get minus 450. We can update the theta naught value. Theta naught value is the previous theta naught minus alpha into 1 by m into the total error. Total error that just now we have calculated is minus 291. And from that we will get 1.7275, and theta 1 similarly we get 4.875. This is after one iteration. These are the theta naught, theta 1 values, and for the initial values, if you take the cost function, that is 2110 point, and in the after first iteration you get this theta naught theta 1 values, and the cost function is reduced. And in the second iteration we will get 2.296 and 6 point with a similar steps, and after some number of steps it will converge to the solution that we got by using a direct approach, that is theta naught as 42.5 and theta 1 as 7.0. Okay, so now we have to define little bit about the convergence. Here the convergence is defined based on either the number of iterations, that means after some number of iterations we are going to stop it, or within some threshold. If j of theta is within some threshold, you are going to stop it. Something like if j of theta is less than 0.5, then stop it. If j of theta is less than 1.0, stop it. Something like that. So if j of theta is within some threshold, we can say that it has converged to a solution, or do it some number of iterations, then we say that it has converged to a solution. Okay, so this is how the gradient descent works, and this is very popular approach and used in almost all machine learning algorithms. Okay, and we will see a practical implementation of gradient descent in the next lecture. Thank you.